Okay, let's continue. So what we have seen so far is basically a general solution of recurrence. A plug-in chuck is very powerful. You can basically solve this for any recurrence that you encounter. But the problem is sometimes there are a specific form of recurrence and then a specific way of solving it that result in a very simple method. This is what we are going to see later. Yeah. So this is basically the next part. The next part we are going to see linear recurrences. Yeah. So we are going to see linear recurrence and how to solve them. So I don't want to show you this one. We just continue with the recurrence. This is a recurrence. Look at this recurrence. The recurrence is f0 is equal to 1, f1 is equal to 1, and fn is equal to fn minus 1 plus fn minus 2 for all n larger or equal to 2. Okay? Now, what do we have here? This is another recurrence here. This recurrence is quite peculiar because we have two boundary conditions here. It's okay. We will see later on that if we have two functions on the right side here, then we will indeed need two boundary conditions. Now, such recurrence here is called a linear recurrence. Why is it a linear recurrence? Because the parameter here reduces linearly. Originally it is n, this becomes n minus 1 and n minus 2. So if it ends minus something, n minus something, n minus something, this is what we call a linear recurrence. But if it is n divided by something, then this is no longer a linear recurrence. We call this usually a divide and conquer recurrence. So let's continue. And this is called a Fibonacci recurrence. Now, the problem is, how do we solve this recurrence? Let me again remind you, a recurrence is called linear if it is minus something. So this is the parameter here, n, then it is n minus 2, for example, then this will be a linear recurrence. Okay. How do we solve this recurrence? The recurrence that we have just seen is called a homogeneous linear recurrences. A homogeneous linear recurrence has these general forms. Fn is equal to a1, this is called coefficient, fn minus 1. You always start from n minus 1, plus a2 fn minus 2, and so forth, until AD Fn minus D. And you have to list them, n minus 1, n minus 2, n minus 3, n minus 4, n minus D. Okay? Now, what if you don't want the n minus 1 part? If you don't want it, then it is simple. You just set A1 is equal to 0, and it will just disappear. But still, yeah, still actually there are D terms here. First one, second one, and the dth terms. A1, A2, AD, and D are all constants. Okay. Now, for this linear recurrence, we call the order. The order of this linear recurrence is D. What is the D? The D is basically the summation here, the reduction. The largest deduction. N minus D, then the order is equal to D. So when D is the largest. Yeah? Usually, a couple of values in the beginning also explicitly specified, and we call this the boundary conditions. How many boundary conditions do we need? If we have a linear recurrence of order D, then you will need D boundary conditions. Okay. How do we solve this such recurrence? Well, to solve this recurrence is like this. Remember this. Any linear recurrence, every linear recurrence always have an exponential solution. Yeah? So every linear recurrence always have such solution. So that means if you are given a linear recurrence like this, then you have to guess. Guess that the solution will be of the form fn is equal to x divided by n. What is x? I don't know. This is basically what we are going to find out. X is the one that we are going to find out. Okay, so we guess that the solution is always x to the power of n, but we don't know what is x yet. We are going to find out what is x. Okay, this is the how to solve the solution. So let's apply this to our problem. In our problem, fn is equal to fn minus 1 plus fn minus 2. This is the main recurrence. So what happens? What is the solution of this? Like I said before, just guess. Guess the solution will be fn is equal to x to the power of n. What is x? I don't know what x is right now. Okay, but if fn is equal to x to the power of n, then this, look at this, fn will be replaceable by x to the power of n. But if fn is equal to x to the power of n, what will be fn minus 1? Well, fn minus 1 will be equal to x to the power of n minus 1. You see, everything can always be replaced. If n here, you replace this by n minus 1, you just replace this n minus 1. What about fn minus 2? It is the same. Fn minus 2 will be equal to x to the power of n minus 2. So this recurrence here becomes this equation. X to the power of n is equal to x to the power of n minus 1 plus x to the power of n minus 2. Okay. So what do we do next? Well, this is very large equation, but if you see, if I divide the left hand side and the right hand side by this power, the smallest power, x to the power of n minus 1, then I can actually simplify this equation. You see, divide the right hand side and the left hand side by x to the power of n minus 2. This one divided by x to the power of n minus 2. What is left? X to the power of 2. What about this one? This one divided by x to the power of n minus 2. What is left? X. This one, x to the power of n minus 2 divided by x to the power of n minus 2. What is left is 1. So this is our equation. You see, it is much simpler than now. This is just a quadratic equation. X to the power of 2 is equal to x plus 1. What is x right now? So you see, what we are going to find is actually x. Well, if this is the equation, we call this the characteristic equation. So how do we find x right now? Find the root of this equation. Find the root of this equation. Well, how do we find the root? You know how to find the root of quadratic equation. This is the root of the quadratic equation. X1, by using ABC formula, basically. X1 is equal to 1 plus the square root of 5 divided by 2. X2 is equal to 1 minus the square root of 5 divided by 2. So we have a problem right now. There are two x's. If there is only one axis, then our problem is already solved, because we guess fn is equal to x to the power of n. But actually, right now, there are two x's. There are two possible solutions. What do we do if we have two possible solutions? So there are two possible solutions. The first one is fn is equal to 1 plus the square root of 5 divided by 2 to the power of n, because what we have just found is x. And another one is fn is equal to 1 minus the square root of 5 divided by 2 to the power of n. How do we deal with this one? Well, we have this theorem. The theorem says that if Fn and Gn are solutions of homogeneous linear recurrence, then Hn, which is equal to S multiplied by Fn plus T multiplied by Gn, this is supposed to be Gn, careful about this one, yeah? Note this, I'm sorry for the mistake, for all S and T element of the real number. So that means that if Fn is a solution, Gn is a solution, then all of their linear combination, you've already known linear combination from previous meetings, I think, then all of the linear combination will also be a solution. Yeah? So this theorem basically says that if F is a solution, G is a solution, then all of their linear combination which will also be a solution. So that means that the solution is like this one. Fn is equal to S multiplied by the first solution, 1 plus the square root of 5 divided by 2 to the power of n, plus t multiplied by 1 minus the square root of 5 divided by 2 to the power of n. But we don't know what S and T are. S basically can be any real number. T can be any real number. Okay? Now, but of course, if this is the case, then the number of solutions will be infinitely many. There are many possible S. There are many possible T. How do we fix this? Like the previous one, we fix this by using what we know. What do we know? The boundary condition. Yeah? What we know is the boundary condition. What is the boundary condition? Well, use your boundary condition right now for all of these possible or limitless possibility. There are many, infinitely many possibilities. There are infinitely many solutions. We find the one that satisfies the boundary condition that F0 is equal to 1 and F1 is equal to 1. So this is easy then. Just fix it. F0, that means the power is n, Fn is equal to S multiplied by 1 plus the square root of 5 divided by 2 to the power of n. So this becomes 0 here, this becomes 0. S multiplied by this one to the power of 0 plus t multiplied by this one to the power of 0. Well, something to the power of 0 is always 1. This is 1, this is 1. So this becomes S plus t is equal to 1. F0 is equal to 1. So you have this one equation. Okay. Now, what else? Another one is F1. What is F1? F1 is S multiplied by 1, this one to the power of 1 plus t multiplied by this one to the power of 1, and this is equal to 1. So you have here right now two equations. This one equation, two equations, and these equations are linear equations. So you have a system of linear equations. You have a system of linear equations. You know how to solve a system of linear equations to find S and T. You can use Gaussian elimination, anything. Yeah, you can use anything, any method to solve the system of linear equation. And the solution for S and T, you can try it yourself. This is the solution for S. S is 1 divided by the square root of 5 multiplied by 1 plus to the square root of 5 divided by 2. And T is minus 1 divided by the square root of 5 multiplied by 1 minus the square root of 5 divided by 2. Okay? So the final solution will be this one. S multiplied by this one. What is S? S is this one multiplied by 1 plus the square root of 5 divided by 2 to the power of n. And this is T multiplied by 1 minus to the square root of 5 divided by 2 to the power of n. And this is the final result. Even though this formula looks complicated, this is a closed form solution. If I ask you right now, what is F100? You can simply substitute n by 100 and you will be able to find the solution. And even though this looks really complicated, the solution will be an integer. Okay? The solution will be an integer. Okay, let me continue. We don't have much time. Uh, well, I show you the solution by using an example. Right now, I'm going to show you, I'm going to basically tell you the general solution. So any homogeneous linear recurrence has this form. This is the general form of homogeneous linear recurrence. Fn is equal to a1 fn minus 1 plus a2 fn minus 2 and so forth until ad fn minus d. Okay? Now, how do we solve this? The first step is guess that fn is equal to x to the power of n. If this is the case, then you will always be able to replace this fn by using this one. Fn is equal to x to the power of n. Fn minus 1 is equal to x to the power of n minus 1. So this equation here, this recurrence becomes this equation. X to the power of n plus a1 multiplied by x to the power of n minus 1 plus a2 multiplied by x to the power of n minus 2 and so forth until ad multiplied by x to the power of n minus d. Divide the left hand side and the right hand side by the smallest power, x to the power of n minus d, and this is the solution. X to the power of d is equal to a1 x to the power of d minus 1 plus a2 multiplied by x to the power of d, there's something wrong here, x to the power of d minus 2, and so on until ad. Now, this is called a characteristic equation. If you have already found the characteristic equation, the next step to find x will be just to find the root of this characteristic equation. So the solution of the recurrence is defined by the root of this characteristic equation. But you have to be careful about this. Now, the root may be non-repeatable. In our previous example, there are two roots, and this root are non-repeatable because the first one is only one root of this form. The second one also is only one root of that form. So if it is not repeatable, then r to the power of n is the solution. Like the previous one here. There are two roots here. Yeah, there are two roots, x1 and x2. So take the first root to the power of n, take the second root to the power of n, both are solution because they are not repeatable. What if they are repeatable? If r is a repeatable root, then, yeah, and the repeatable is of multiplicity k. What does it mean? There are k times a particular root. K times a particular root. Then r to the power of n, the next one, n multiplied by r to the power of n. So this is not enough just r to the power of n, because if it is just r to the power of n k time, then the whole thing will be just disappear. So you have to multiply r to the power of n. The second one is n multiplied by r to the power of n. The second one, the third one is multiplied by n again, n to the power of 2 multiplied by r to the power of n, and so forth until n to the power of k minus 1 multiplied by r to the power of n. All of them are the solution of the recurrence. Let me give you an example. Assume that once you find the characteristic equation, we have four roots. The first root is r1. The second root is r3. And the third root is r3. Sorry, the second root is r2. The third root is r3. And the fourth root is also r3. So there are r3 occurs twice. So that means the solution will be r1 to the power of n, because it only occurs once, it's enough, r to the power of n. R2 also occurs once, it's enough, r2 to the power of n. The third one will be r3 to the power of n. What about the fourth one? The fourth one is not r3 to the power of n, because if it is just r3 to the power of n, it will just disappear. So you have to multiply it by n. The fourth one will be n multiplied by r3 to the power of n. Okay? So be careful about that. Yeah? So if this is a solution, then their linear combination will be a solution. What is the linear combination? S multiplied by this one, plus T multiplied by this one, plus phi multiplied by this one, plus U multiplied by this one. All of this will be just a solution. Yeah? The solution for all possible S, T, V, and U. Okay. So once you find this, the last step is to find the solution, a solution, because when we are seeing this solution, the solution is infinitely many. This is possible for all possible S, for all possible T, for all possible phi, for all possible U. But our solution must not be that. Our solution must be consistent with the boundary condition. Put it, the boundary condition. Put the boundary condition, apply the boundary condition to form a system of linear equation. Now the solution of this system of linear equation will give you the coefficient. What it will be S, what will be T, phi, and U for that particular combination, linear combination. Okay? So that's it for homogeneous linear recurrence. Now, if you have questions right now, just raise your, the questions so that we can continue. If not, then I'll just continue with the inhomogeneous linear equation. I'll just give you 1 minute's time. Okay, let's continue. So, this is the general solution of homogeneous linear recurrence. So if there is a homogeneous linear recurrence, there must be something that is not homogeneous. Yeah. So we are going to see this. This is called a general linear recurrence, or inhomogeneous linear recurrences. What is the difference between homogeneous linear recurrence and the general linear recurrence? The only difference is that on the inhomogeneous linear recurrence, there is something here that is not a form of the recurrence. So this is a recurrence. Fn is equal to A1 Fn minus 1, A2 Fn minus 2, and so on until AD Fn minus D. And there is something left here of another function. This cannot be another f, but must be another function. Now, if there is an addition here, another function, then this is called an inhomogeneous linear recurrence. So, because it is no longer homogeneous. You see? So, A1, A2, until so on until AD and D are all constants. So how do we solve this? The way to solve this is just similar to the way we solve homogeneous linear recurrence. In the first 3 steps, you just pretend that it is homogeneous. So this means that forget about this in the beginning. Okay? So there are five steps to solve this. The first one, find the roots of the characteristic equation. So the previous one is just applies. Basically, assume that the solution is Fn is equal to x to the power of n, and therefore we find the characteristic equation, and this is the characteristic equation. Okay? Now, if this is the characteristic equation, then there must be a root. Now, once you find the root, then there must be a solution of this root. A solution of this root is basically what I mean before by linear combination of them. And we call this the homogeneous solution. Write down the homogeneous solution of this recurrence. Every root results in one term in the solution. Unrepeatable root will result in C multiplied by R to the power of n. If it is repeatable with multiplicity k, then we will have this d1 multiplied by R to the power of n, and so on, like I showed you previously. This is what we call the homogeneous solution. So in the beginning, you just pretend basically that this one is not there, that the whole recurrence is just a linear one. Okay, now let's continue. And then, now this is something new right now. Find the spatial solution. What is the spatial solution? This is the solution that has something to do with these inhomogeneity. The inhomogeneity is basically arises out of this function Gn. So you will try to do this. So use the guess and verify. If Gn is a polynomial, you know a polynomial? A polynomial is n to the power of something plus n to the power of something or something like that. You know, if it is a polynomial, then use a polynomial of the same degree. If you cannot find a solution, use a polynomial of higher degree, and so on and so on. For example, if Gn is equal to n, then the degree of this n, the degree of this polynomial is equal to 1. So if this is the one, then use guess. Your guess will be, the solution will be Fn is equal to Bn plus C, where B and C are all constant. So this is the general degree 1 polynomial. But if this does not result in a solution, then guess something of higher degree. The next higher degree will be Fn is equal to n to the power of 2 plus Bn plus C, and so on. If it does not work, then you guess Fn is equal to n to the power of 3 plus Bn to the power of 2 plus Cn plus D, and so on. Okay? Now, let's continue. What if Gn is not a polynomial, but if it is an exponential function? For example, it is of the form d to the power of n. Then the first one, try just multiply it by a constant c. C multiplied by d to the power of n. If it does not work, then try multiplying it by a linear function, bn plus c multiplied by d to the power of n. If it does not work, multiply it with a quadratic equation, an to the power of 2 plus bn plus c multiplied by d to the power of n, and so on. This is what we call a spatial solution. Okay, let's continue. The fourth step is just the general solution is the homogeneous solution plus the spatial solution. So you just have to add them together. Add the two solutions. Add the homogeneous solution to the spatial solution. And then the fifth one, what do we have here? The fifth one is just applying the boundary condition to the general solution. Applying the boundary condition like I have shown you before. Once you apply this boundary condition, then you're supposed to be able to find all of the constancies. Yeah? So, let me give you an example. We are asked basically to solve this recurrence. F1 is equal to 1, Fn is equal to 2, Fn minus 1 plus n. So this is not a homogeneous linear recurrence, because here there is a function. The function gn is equal to n. This is not. This is an inhomogeneous linear recurrence. Okay? So how do we solve this? To solve this, first pretend that this is a homogeneous linear recurrence. So this n here, you just you just pretend that this is not there. So what is the characteristic equation of this one? Well, the characteristic equation is, well, guess fn is equal to x to the power of n. So if this is x to the power of n, so this is x to the power of n is equal to 2 times x to the power of n minus 1. Yeah? So this one is not there because you just have to find the characteristic equation first. So x to the power of n equal to 2 times x to the power of n minus 1. So divide the left-hand side and the right-hand side by the smallest power. The smallest power is x to the power of n minus 1. So the result will be this one. X is equal to 2. So this is the root. X is equal to 2. So there is only one solution. X is equal to 2. You see? So what is our solution there? Our solution, this is called the homogeneous solution, is Fn is equal to C multiplied by 2 to the power of n. The C here is a constant. Yeah, because of course you are still have to take all of the linear combination. So our solution is 2 because x is 2. We have already guessed here that the solution is x to the power of n, and x is equal to 2, so 2 to the power of n, and then you multiply it by something, some constant. We don't know this constant yet. We have to use the boundary condition to find this constant. Okay, c multiplied by 2 to the power of n. This is what we call a homogeneous solution. Okay, now let's continue. Now once we find the homogeneous solution, we have to find the spatial solution. Remember that the inhomogeneity arises from this one. The function is gn is equal to n. So our function is equal to gn is equal to n. If this is the case, according to the rule, then I will basically guess that the solution is given by Fn is equal to An plus B. This is a linear function, A multiplied by N plus B. I don't know what the constant A and B are, but we are going to find out. Okay? So, Fn is equal to An plus B. Yeah? Take the main recurrence. Fn is equal to 2 Fn minus 1 plus n. So Fn is equal to 2 Fn minus 1 plus n. Okay? We know this. This is the main recurrence. What do we have to do next? Well, we know that Fn is equal to An plus B, so you just replace it. Fn is equal to An plus B. What about Fn minus 1? Well, Fn minus 1, if you replace this by n minus 1, then you have to just replace this one also with n minus 1. So this will be 2 times An minus 1 plus B. Yeah? So you see, this is just basically replacing things. Plus 1. Okay? So look at this. And all you have to do right now, once you find this one, is to simplify it. How do you simplify this? You simplify it by collecting all n's, then all constancies. By collecting all n's and all constants. I will have to, I think, help you with this one. So I'm going to show you here. Show you in the Excel. Okay. So we have it here. Look at this one. N plus B is equal to 2 A n minus 1 plus B plus n. What do we do right now? The easiest to do is to move all of these things to the left. And this will be an plus b minus 2an. Multiply this right away, 2an. Yeah? And then minus 2a minus 1. So minus 2a. Yeah? And then remember again also that this is 2 times b. But when you move this to the left, this will becomes minus. Yeah? Minus. Minus 2an. And because this is a minus, this will become plus 2a. And this is minus, this is a plus here, plus 2b. So this is minus this minus 2b. And then this is minus n is equal to 0. Okay? What else can we do right now? Collect all that is multiplied by n. an minus 2an minus 2an. So, wait a minute. I think I just made a mistake. This is not there. Huh? So, an plus b minus 2an plus 2a minus 2b plus minus n is equal to 0. Okay. Now, an minus 2an minus n. Okay. And then collect all the rest plus b plus 2a minus 2b is equal to 0. Okay. So what else can we say about this? This is an minus 2an. So this will be minus an minus n. Yeah? Plus 2b minus b is equal to 0. Yeah? Minus an. No, so I just put it like this. N multiplied by minus a minus 1 plus 2a minus b is equal to 0. This one is a. Okay. So n multiplied by minus a minus 1 plus 2a minus b is equal to, now this is the catch, is equal to 0 multiplied by n plus 0. So actually this is just equal to 0, but I can just say that this is equal to 0 multiplied by n plus 0. It's just the same. So that means I can right now say that n times something here. What is the something? This is 0, and this one also is equal to 0. So the consequence is of this is minus a minus 1 is equal to 0, and minus a minus 1 is equal to 0. And another one is 2a minus b also is equal to 0. This is a system of linear equation again. You're supposed to be able to find what is a, what is b, and so forth. Okay. Let me return to the slide. Yeah? So this is equal to 0, a plus 1. I don't know. I think I just made a mistake there. An minus, I don't know. I mean, just look yourself. I don't. There may be a mistake that I have made in the previous slide. or you can just move this around. I think this is the one that is good. Yeah. So basically, if this is equal to 0, 0 is equal to a plus 1 multiplied by n plus b minus 2n. And then the last equation is basically applies for all n. So that means that a plus 1 is equal to 0. Yeah. So that means that a is equal to minus 1. And then b minus 2a. I think both of them are just fine. Yeah. The previous one is just fine. Also, this one is also fine if you find if you perform the computation. And b minus 2a is equal to 0. So that means b is equal to minus 2. Therefore, the 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 spatial solution is equal to fn is equal to an plus b. This is our guess. Just replace this a by minus 1, so minus n minus 2. Okay, so let's continue. The first step, just add them together. So the general solution is the homogeneous solution plus the spatial solution. So fn is equal to c multiplied by 2 to the power of n minus 2. You see? So that's it. The only thing left for us to do is to use the boundary condition. The boundary condition is f1 is equal to 1. So how do we do that? Well, just add f1 is equal to 1. So f1 is equal to this one. f1 is c multiplied by 2 to the power of 1 minus 2. So this is equal to 1. So 2c minus 3 is equal to 1. So c is equal to 2. So based on this, we know what is 2. 2, yeah? Sorry, what is c? C is equal to 2. So fn is equal to 2 times 2 to the power of n minus 2. And the final solution is fn is equal to 2 to the power of n plus 1 minus n minus 2.